Welcome. The presentation you're about to watch is called the fractal algorithm, and the title is deliberate. A fractal is a pattern that repeats itself at every scale of magnification. And as we'll see and discover over the next 35 minutes or so, that's exactly what's happening inside the modern large language models. At the largest scale, the database level, AI system need to search through billions of documents to find the handful most relevant to your query. At the smallest scale, inside every single layer of the transformer, the model is doing something mathematically identical, just on token vectors instead of the documents. The same geometric algorithm, nearest neighbor search, runs the show at both the levels. That's the fractal, and understanding it changes how you think about AI scaling. This presentation covers three interconnected ideas. First, vector embeddings and high dimensional space, how language gets turned into geometry. Second, the approximate nearest neighbor search, or ANN, the algorithmic trick that makes searching billions of vectors feasible. And third, retrieval augmented generation, or RAG, how these ideas combine to let language models work with knowledge bases far too large to fit in memory. By the end, you won't just understand what these systems do, you'll understand the deep mathematical reasons why they work and why the future of AI scaling is more about geometry than it's about raw compute. Let's begin. In a perfect world, we would have an algorithm that uses minimal space and provides near instant query times. However, the nearest neighbor search faces a fundamental challenge known as the curse of dimensionality. In practice, there are two extremes of indexing. The first is no indexing, where we are underprepared and must scan the entire database for every query. This is linear in time, meaning if you have a billion documents, you check a billion documents. The second is full indexing, which is lightning fast but requires exponential space, effectively trying to map out every possible query in advance. Theoretical computer science tells us that under the strong exponential time hypothesis, we cannot hope to solve this problem perfectly in high dimensions without succumbing to one of these two extremes. If you want to scale AI to handle the world's data, we cannot be perfect. We must instead look towards approximation, relaxing our requirements to find something sufficiently similar rather than the absolute closest point, allowing us to break through these theoretical barriers and achieve sublinear query times. The high dimensional space. Imagine a library with a billion books. N is equal to 1 billion. Now imagine each book isn't on a shelf, but is a single point in 1000 dimensional space, where d is equal to 1000. This is deep embedding. We map semantic meanings like the relationship between the king and the queen into geometric coordinates. The core problem, when you ask a question, the AI answering it has to find the closest semantic match. This is nearest neighbor search. The challenge, you have to find that one specific point, the needle in the haystack, without scanning the entire universe of data. Visualizing dimensions. We can only visualize 3D, but math works in 1000 dimensions. In that space, distance represents meaning. If 2 points are close, they are semantically similar. But there's a catch. In high dimensions, the traditional math starts to break. This is what we call the curse of dimensionality. Let's establish the scale of the problem we are solving. Imagine a database with 1 billion vectors, that's n equals to 1 billion. Each of those vectors has 1000 dimensions and d is equal to 1000. These numbers aren't hypothetical. They are representative of production AI systems like those powering Google search or ChatGPT's retrieval layer and enterprise knowledge bases. What's a vector? When a language model reads a sentence, it doesn't store words. It stores a list of numbers, 1000 numbers in this case. This list is a point in 1000 dimension space. Semantically similar sentences end up as geometrically nearby points. The cat sat on the mat, and another sentence, a feline rested on the rug, would be close together. Quarterly earnings report would be far away from this sentence. However, here's the problem. When a user asks the question, the system converts that question into a query vector. It then needs to find the vectors in the database closest to that query. The semantically most relevant documents. Simple enough is the concept. But Brute force is of O of n times d for a billion vectors at 1,000 dimensions each. That's 1 trillion arithmetic operations per query. At modern CPU speeds, that's several seconds per search. At millions of queries per day, that's physically impossible. The core insight on this slide, and the one that drives everything that follows, is this: we need to find the target without scanning the entire universe. That challenge is the engine of everything we are about to explore. Now, how do we escape the curse of dimensionality? There are three approaches. There are three ways to find our needle. The first is lazy approach, no indexing. We check every single point one by one. For a billion points, this is computationally impossible. That's too slow. The over-prepared approach, this is full indexing. You try to build a perfect map of everything possible, the relationships, but in high dimension, this space needs for the map grows exponentially. It would literally break physical hardware limits. The pragmatic hero, that is the approximation. We surrender absolute exactness. Instead of finding the perfect neighbor 100% of the time, we find very good neighbor 99% of the time. This exchange gives us exponential speedups and sublinear search times. To make AI fast, we have to be okay with being slightly wrong to be massively faster. Again, to dwell in a bit deeper, there are three philosophies for solving search problem, and in this slide, lays them out side by side. Understanding why the first two fail is just important as understanding why the third one works. No indexing, just scan everything. Space cost is low, but you're not building any index structure. But the query is O of n times d. We already established that it's impossible at scale. This is the lazy approach. It works for toy datasets. It fails catastrophically for production systems. Philosophy 2, full indexing. Build a perfect index that answers every possible query in constant time. Sounds ideal? The problem is space. For d-dimensional data with approximate tolerance epsilon, the required index size is O of n to the power of d over epsilon. In 1,000 dimensions, that exponential blows up to a number larger than the number of atoms in the observable universe. Physical hardware limits make this completely impossible. This is the curse of dimensionality. The name mathematicians give to the counterintuitive fact that high dimensional spaces are incomprehensibly large. Philosophy 3, approximation. And this is the pragmatic hero of our story by accepting that our search might occasionally return a result that's very close but not probably the absolute closest. We unlock an entirely different complexity regime. Near linear space, sublinear query type, mathematically bounded error. This isn't a hack, it's an elegant theoretical result. The key word is bounded. We're not throwing up our hands and saying close enough. We are making a precise mathematical guarantee. The result will be within c times the true nearest distance for some approximation factor c. That precision is what separates principled approximation from random guessing, and it's what makes the whole system trustworthy at scale. The C approximate loophole. Since exact search is computationally hard, we shift our focus to approximate nearest neighbor search, or ANNS. In this framework, we define a threshold of similarity, which we call the radius R. If a point falls within this green safe zone, it's a good answer. To make the math work, we introduce a no man's land, a gray band extending to a larger radius, CR, where C is our approximate factor. Our algorithm's job is simple. If there's a point in the inner green ball, it must return something from the larger gray ball. If there's nothing, even in the larger gray band, it can support that no neighbor exists. This slight relaxation, accepting a point that is close enough, is the key to efficiency. In practice, these algorithms act as high-speed filters. They quickly narrow down a billion possibilities to a few candidates that are likely to be similar, which we can then double-check for exactness. By calibrating the right radii, we transform the impossible search into a manageable filtering task. Now, let's formalize it. Let's formalize the approximation idea with the visual on the left. Picture a query point Q sitting in the center of the three concentric zones. The innermost zone, the green circle with the radius R, is the definite similarity zone. If a document vector lands here, it's genuinely close to the query. The algorithm must find it. The outermost zone, the large circle, is the definite dissimilarity zone. Vectors out here are genuinely far away from the query. the algorithm must not return them. In between is what we call in the slide no man's land, a kind of gray band which we saw in the previous slide between the radius r and the radius c times r, where c is our approximation factors, say 2. Vectors in this zone are ambiguous, they're not obviously close and not obviously far. Here is a loophole. The C approximate nearest neighbor guarantee says if a vector exists in the green zone, the algorithm is allowed to return any vector from either the green zone or the gray band. It's never allowed to return something from the outer ring of the definite dissimilarity. This sounds like a small concession. It is actually enormous. By allowing the algorithm to be a little lazy about the boundary cases, the gray band, we give it permission to skip the expensive exact comparisons that make brute force so slow. The algorithm can now prune entire regions of space without checking every point inside them. The mathematical insight is that introducing bounded non-determinism at the boundary collapses the query from Q of n to sublinear. That's not a minor speed up, that's a difference between a search that takes 3 seconds to one that takes 3 milliseconds. Locality sensitive hashing, also abbreviated as LSH. Now we have a specific algorithm, locality sensitive hashing. It is the theoretical foundation for achieving C-approximate search in practice. The core idea is elegant. A hash function normally maps inputs to random looking buckets. Two similar inputs end up in completely different buckets. A locality sensitive hash function inverts this. It's specifically engineered so that the similar inputs land in the same bucket with a high probability and dissimilar inputs land in different buckets. The common approach uses random projections. You project your high dimensional vector into random low dimensional grid. The grid cell, a vector lands in its hash bucket. Because the nearby vectors project to a nearby grid positions, they end up in the same bucket. Because distant vectors project far apart, they end up in different buckets. Here's the indexing trick. At query time, you hash the query vector and only retrieve documents from the same bucket or nearby buckets. You completely skip the other 999,900,000 vectors. That is the speed up. The theoretical bound is particularly beautiful. The probability of collision, two vectors landing in the same bucket, turns out to be inversely proportional to their distance, with an exponent equal to 1 over c squared. This means query times drop to O of the square root of n for c equals 2. For billion vectors, that's a 30,000 times speed up over brute force. In practice, you run multiple hash tables with different random projections to boost recall. The probability of catching the true nearest neighbor. Each additional table costs memory but improves accuracy. The design becomes a tunable trade-off between speed, memory, and recall quality. Macro-scale retrieval augmented generation RAG. Now let's see how this geometry powers the LLMs we use every day through retrieval augmented generation or RAG. One major limitation of models like ChatGPT is the context window. You cannot feed 1,000 books into a single prompt. RAG solves this by using a two-step pipeline. First, all your documents are pre-processed into vector embeddings and stored in a retrieval system. When you ask a question, the system doesn't search the text. It performs a nearest neighbor search query in the embedding space to find the top k most relevant document snippets. These specific snippets are then fed into transformer context. This allows the model to know information it wasn't originally trained on. Essentially, the quality of an LLM's answer in a RAG system is directly dependent on the efficiency and accuracy of the underlying nearest neighbor search. We are moving from models that know things to models that find things. The problem of finite memory. LLMs have context windows. They can only read so much at once. You cannot feed an entire billion document library into a prompt. We use the NNS as we just learned. We pre-process and embed the entire corpus. When you ask a question, the NNS filter acts like a funnel pulling out the top k most relevant documents. Notice how the massive corpus is narrowed down into a few pages of context before it even hits the transformer block. This makes the AI smarter without making the model itself larger. This is the macro scale of our fractal. It is the external memory of the AI. It's like a pen drive plugged in. Let's dwell in a little more deeper. Now we zoom out to the application layer. How does all this vector search theory connect to the language models that millions of people use every day? The answer, as we just discussed, is retrieval augmented generation. Look at the flow across the top of this slide. A prompt arrives, it passes through the nearest neighbor filter. The filter queries the corpus of 10 plus billion documents. It extracts the top k most relevant items. Those items become the context window fed to the transformer. The transformer generates the final response. The transformer architecture, to be precise, of the LLM. The problem this solves is fundamental. Context windows are finite. A transformer can process perhaps 100,000 tokens at once. Call it 300 pages of text. Your enterprise knowledge base has 3 million documents. You cannot fit the knowledge base into the context window, not even close. Without RAG, the model can only use knowledge baked into its weights during training, which may be months or years out of date, and which can't include your proprietary internal data. With RAG, the model dynamically retrieves relevant documents at inference time. It knows about last week's earning report. It knows about your internal product specification. It knows about research published yesterday. The solution is to pre-process and embed all documents, run them through an embedding model to generate a vector per document, and store these vectors in a vector database. At the query time, the nearest neighbor search, or NNS, finds the most relevant vector in milliseconds. The transformer sees a curated relevant context instead of everything. This is why vector search infrastructure companies like Pinecone, VV8, and Chroma have exploded in value. RAG is not a nice to have. For enterprise AI that needs to work with current proprietary or specialized architecture knowledge, it is the architecture. The vector search reality, theory versus practice. While locality sensitive hashing is great in theory, the industry has largely pivoted to a different style of search, graph-based algorithms, specifically HNSW. Instead of buckets, we build a graph where every data point is node connected to its closest neighbors. To find a neighbor, we start at a random entry point and perform a greedy walk, always moving to the neighbor that is geographically closer to our query point. These graph-based methods are currently the fastest practice and are used by the major vector search companies. However, they present a fascinating theoretical mystery. They can sometimes get stuck in local minima if the graph isn't perfectly constructed, while theory suggests that they work best on data with small doubling dimensions, meaning data that lives on a simple low-dimensional manifold. It is still not fully understood why they perform so exceptionally well on complex deep embeddings produced by modern AI. Bridging this gap between the graphs work in practice and how we prove their success in theory is one of the most exciting open questions in the field. We just talked about locality sensitive hashing. It's great for mathematicians because it has provable worst case bounds. We understand the math perfectly, but in real world it can be a bit slow. The HNSW, that is the hierarchical navigable small worlds. Instead of grids, HNSW uses graphs. It navigates by jumping from point to point, like following a social network to find a friend. The HNSW is extremely fast empirically, but it lacks the strict mathematical bounds of LSH. It works in practice, but not in theory solution that dominates industry data pipelines. Theoreticians use grids, engineers use graphs. Let's move a little more deeper. Vector search reality, theory versus practice. There's a gap between what computer scientists study and what engineers actually deploy. This slide is about that gap. On the left, the LSH, the theoretical computer science standard, it provides provable worst case bounds. You can mathematically certify that query time will never exceed a certain threshold. It partitions space via geometry, dividing the space into cells like a grid. It is mathematically elegant and rigorously analyzed, but in practice, its empirical performance and real embedding data is often mediocre. On the right, HNSW, the abbreviation for hierarchical navigable small world graphs. This is what virtually every production vector database uses today. Pinecone, VV8, Milvus, PGVector, they are all running variants of HNSW. It dominates industry data pipelines. HNS-W navigates space the way you would navigate a city with a map hierarchy. At the top level, you have a coarse graph, major landmarks. You navigate to the rough neighborhood of the query. Then you drop a finer level and navigate to the right block. Then finer still until you converge to the nearest neighbor. This hierarchical point-to-point navigation is extremely fast in practice. The catch: HNS-W lacks strict theoretical guarantees. There are edge cases where it gets stuck. The query time is not provably bounded in the worst case, but empirically it achieves greater than 99% recall at under 10 milliseconds on billion scale datasets. For engineers, empirical performance beats the theoretical elegance. The synthesis at the bottom captures the tension beautifully. While theoreticians partition space with grids, industry navigates space point to point via graphs. Both are valid approaches. They just are optimized for different definitions of success. As we just discussed, the routing rule in graph-based search like HNS-W, the rule is simple: always move to the neighbor physically closer to the query, the failure state. But what if there's a missing edge? Look at the red X in the diagram. If the graph isn't perfectly connected, the search gets trapped in a local minimum. It thinks it's as close as it can get, but the true neighbor Q is just on the other side of the gap of a gap. This is a huge area of research. Does deep embedding data have a small doubling dimension that naturally prevents these traps, or we are just getting lucky? If you get trapped, you might have to scan the whole database anyway, which is the worst case we are trying to avoid. HNS-W works spectacularly well in practice, but it has a known failure mode, and this slide explains it perfectly well. The routing rule in any graph-based search is simple: always move to the neighbor geometrically closest to the query. From your current node, look at all your neighbors, move to whichever one is nearest to the query vector. Repeat until no neighbor is closer than you are. This is greedy strategy, and it is fast, but greedy strategies can get trapped. Look at the graph visualization on the left. The algorithm starts at the top left and correctly routes towards the query at the bottom right. But at some point it reaches a node that has no neighbor closer to the query than itself. Yet the query is still far away. The algorithm is in a local minimum. From where it stands, every step looks like a step backward. But if the graph had a long-range edge, a shortcut across the graph, the algorithm could escape and continue towards the query. The X on the slide marks where this crucial edge is missing. The failure state is stark. If the graph lacks the right connecting edge, the search gets trapped in local minimum and in the worst case whelps into an O of n scan. HNS-W hierarchical structure dramatically reduces the probability of this happening by providing those long-range shortcuts at multiple scales. But it cannot eliminate the risk entirely. The open question on this slide is genuinely fascinating. Does deep embedding data inherently possess small world geometric structure, the kind of structure that makes HNS-W work so well? If the answer is yes, and if we can prove it, then HNS-W empirical success becomes theoretically grounded. This is an active area of research at the frontier of geometric deep learning. Beyond Euclidean geometry, Earth mover's distance. Usually we treat a 50-page document as a single point in space, but that is reductive. It flattens competing concepts into a single average, losing semantic richness. Earth mover's distance, EMD. Instead of a point, imagine the document as a cloud of topics. To see how similar two documents are, we measure the minimum cost to move one cloud of info to match the other. This is also known as Wasserstein distance. Topic alignment. This accounts for the weight. If document A mentions AI 90% of the time and document B mentions it 10% of the time, the Earth mover's distance, EMD, recognizes they aren't a perfect match, even if they share same topics. Why it matters? This is the future of rich retrieval, moving beyond simple dots to complex distributions. Now, let's go a little more deeper into the Earth mover's distance. Everything we have discussed so far assumes Euclidean distance, the straight line distance between 2 points in vector space. but Euclidean distance has fundamental limitation when applied to language. Look at the left side of this slide. The naive assumption: a transformer takes an entire document and collapses it into a single vector, one point in thousand-dimensional space. To compare two documents, you measure the distance between their 2 points. Document A is here, document B is there. Distance equals similarity. The problem is that in such an approach is that the rich document covers many topics. An article about climate change might discuss physics, economics, politics, and biology. When you collapse that into a single point, you lose the topical distribution. You lose the internal structure. The single point representation is semantically impoverished. Earth movers distance, also called as Wasserstein distance, offers a richer alternative. Instead of representing a document as a single point, you represent it as a cloud of points, 1 point per topic, weighted by how much the document discusses that topic. Now, comparing two documents becomes a transportation problem. What is the minimum cost to move the Earth of document A's topic distribution to match document B's? This measure is geometrically sensitive to the topical alignment between documents in a way that simple Euclidean distance is not. The mathematical connection is deep. Wasserstein's distance computes similarity by finding optimal transport plan between two distributions over topic vectors, accounting for both alignment and weight. For documents with the rich internal structure, this gives much more semantically meaningful similarity scores at the cost of significantly more computation. It represents the frontier of how we think about document similarity in high-dimensional space. The fractal architecture of AI. We have been talking about two scales, the database level and the attention level, as if they're separate. This slide shows they're the same thing nested. At the top tier, the database level or the macro scale, this is RAG. The system filters through external corpus, potentially billions of documents to find the handful most relevant to the current query. Nearest neighbor search is the engine. The output is the context window fed into the transformer. At the middle tier, the transformer itself, which the slide calls the universal processor. The nearest neighbor search doesn't just feed the transformer, as we are about to see in the next two slides. The nearest neighbor search is the mathematical core of every computation the transformer performs internally. At the bottom tier, the token level, or the micro scale. Inside every attention layer, and a large language model has dozens of them, each token is computing its similarity to every other token. That computation is mathematically a nearest neighbor search over the vector representations of every token in the context. This is fractal. The same geometric algorithm, find the most similar vectors in high dimensional space, runs at the database level, at the layer level, and at the token levels. Scale changes, math is identical. The practical implication of this is profound. Every optimization developed for database level vector search is in principle applicable to the attention mechanism itself. And conversely, understanding the attention mechanism through the lens of nearest neighbor search opens up entirely new approaches to making transformer faster and more scalable. The bottom of the slide states it plainly. Nearest neighbor search doesn't just feed the transformer, it is the mathematical engine inside it. Let's go deeper into the transformer architecture itself. At the heart of every LLM is the attention mechanism. Mathematically, attention can be viewed as vector-valued version of kernel density estimation, KDE, abbreviated. In a standard KDE problem, we want to compute the average influence of a dataset on a query point using Gaussian kernel, calculating how much every key in the database weights against our query. In attention, we do exactly this. We sum up the value vectors, but we weigh them based on how similar the query is to the key. This similarity is often a kernel function of their distance. This means that every time a LLM processes a word, it is essentially solving a massive similarity search problem. Because this is so computationally expensive, researchers are now using nearest neighbor search techniques like important sampling and locative sensitive hashing to speed up this process. Instead of looking at every word in a sequence, we use hashing to only sample the words that matter most to the current query, potentially saving massive amounts of energy and time. Let's look at the attention formula. Softmax of q times k to the power of t, square root of d subscript k into v. This looks like a complex linear algebra, but it's actually a kernel density estimation problem. We are calculating the similarity distance for every token against every other token. The softmax part acts like a Gaussian kernel, weighing which keys are closest to our query. The result is a weighted sum of value vectors. In essence, the AI is asking, based on my current word, which other words in this sentence provide the most density or meaning. This is beautiful math, but it leads us to a massive wall. Let's dwell in a little more deeper. Let's make the mathematical connection between attention and nearest neighbor search explicit. The attention formula is one on the left. Attention of QKV equals to softmax of Q times K transpose divided by the square root of D subscript K multiplied by V. If you have worked with transformers, you have seen this equation, but let's read it differently. Q is the query vector, K is the matrix of key vectors, one per token in the context. The dot product Q times K transpose computes the similarity between the query and every key. Dividing by the square root of D subscript K normalizes for dimensionality. This is exactly the scaling that keeps the attention scores in a range where softmax works well. The softmax converts the similarity score into probabilities, a probability distribution over all tokens. The most similar tokens get the highest weights. The output is then multiplied by V, the value matrix weighted by those probabilities. Here is the KDE connection. This is exactly what the kernel density estimation does. Kernel density estimation estimates the probability distribution by placing a kernel, a smooth bump function, around each data point and summing. The Gaussian kernel is exponential of minus distance squared over 2 sigma squared, and the attention similarity exponential of QK transpose over square root of D subscript K. That is Gaussian kernel in disguise. The direct connection to LSH, locality sensitive hashing. The probability of locality sensitive hash collision between two vectors is proportional to their Gaussian kernel similarity. The math that makes locality sensitive hashing work and the math that makes attention work are the same math. Attention is at its core a differentiable vector valued nearest neighbor search weighted by Gaussian kernel similarities, producing a weighted sum of value vectors as output. The O(n) square wall of exact attention. The attention mechanism is mathematically beautiful. It also has a catastrophic computational cost, and this slide makes that cost viscerally clear. Look at the chart. The horizontal axis is the number of tokens in the context window from 128 to 128,000. The vertical axis is compute time, plotted on a linear scale. As the token count doubles, the compute time quadruples. The curve is a parabola. It is of O(n) squared. Why? Because attention computes the similarity between every token and every other token with n tokens. That's n times the n pairs, n squared comparisons. At 1000 tokens, that's a million operations. At 128,000 tokens, a context window of roughly 400 pages, that's 16 billion operations per attention layer. And a large model has 96 layers. The capacity callout on the right is real. Transformers with full attention can solve k-hop reasoning tasks that require following a chain of k logical steps in O of log k layers. The attention mechanism's ability to attend to any token from any other token in a single step gives its remarkable reasoning power. But the cost is just real. You cannot run a 128,000 token context through a 100 layer transformer in real time. The compute required is physically prohibitive. The verdict at the bottom of the slide is stark. You cannot scale transformers massively with exact attention. We must abandon exactness, and that takes us back to everything we have learned about the approximate nearest neighbor search. The same algorithmic ideas that make billion scale database search possible are exactly what we need to apply to the attention mechanism of the transformer itself. Replacing the core sublinear approximate attention. If exact attention is O(n) squared and we need something sublinear, what do? We apply the same ideas from locality sensitive hashing directly inside the attention mechanism. The left side of this slide shows dense calculation Exact attention. Every query vector computes its similarity to all n key vectors. The dot pattern shows all n times n pairs being evaluated. This is the O of n squared we just saw. The right side shows the sparse bucket sampling. Instead of computing the similarity between a query and all n keys, we first use the LSH to hash the query and all key into buckets. The query only attends to the key in its own bucket, and the highlighted green region, the other keys are skipped entirely. The bucket size is proportional to the square root of n. So instead of comparing against all n tokens, each query compares against roughly the square root of n tokens. Query times becomes O of square root of n sublinear. For a context of 128,000 tokens, that's a reduction from 16 billion to roughly 360,000 comparisons per attention head, a 44 times speed up. This is not theoretical proposal, it is the core idea behind several production attention mechanisms. Reformer uses LSH attention, Big Bird uses sparse attention with random long-range connections, Longformer uses sliding window attention with selective global attention. All are variations on the theme of using structured, geometric, or otherwise to skip most of the attention matrix. The synthesis at the bottom of the slide nails it. Use LSH as a pre-processing step inside the attention layer. You get identical model capabilities, the same expressive power, the same ability to model long-range dependencies at sublinear query time. The fractal algorithm runs at the token level just as it runs at the database level. We have just established that the approximate attention using LSH is theoretically sound and practically fast. There's one more problem, and it's a deeper one. Training. Modern neural networks are trained by gradient descent at each step. You compute how wrong the model's output is, the loss, and then you back propagate. You compute how much each parameter contributed to that error and adjust the parameters to reduce it. This requires that every operation in the network be differentiable, that you can compute its gradient. Here is the catch-22. The operation that makes LSH fast are precisely the operation that lack gradients. Hash functions use discrete buckets. A vector is either in a bucket or it isn't. There's no smooth transition. If-then routing decisions, move to this neighbor, not that one, are step functions. Step functions have zero gradient in almost everywhere and undefined gradient at the boundary. Gradient descent cannot follow through these operations. You cannot train a model end-to-end if the attention mechanism contains non-differentiable LSH components. This is the central unresolved tension in the field. The frontier on the right side of the slide identifies the research challenge. Designing differentiable NNS functions that compute distances effectively without falling prey to the exponential blow-up of the dimensionality. Several approaches are being explored. Soft assignment to the buckets using temperature-scaled softmax. Learned hash functions that approximate locality sensitivity while remaining differentiable. And continuous relaxation of HNSW graph routing procedure. None of these approaches is yet as clean or as proven as the original LSH theory. The differentiability catch-22 is arguably the most important open problem at the intersection of algorithmic efficiency and deep learning scalability. Solving it cleanly would unlock new generation of transformer architectures. Geometry dictates capability. We have covered a lot of ground. Let's bring it together. Takeaway 1. Hardware scales, but the curse of dimensionality is absolute. You can buy more GPUs. You cannot buy your way out of mathematical structure of high dimensional space. A trillion parameter model searching through a billion vectors still faces an exponential space problem if the search algorithm is naive. Hardware is necessary but not sufficient. Takeaway 2. Approximation is not a flaw. It is the key. The C approximate loophole is the fundamental mathematical permission slip that makes modern AI possible. By accepting bounded imposition in nearest neighbor search, we escape the curse of dimensionality. The systems that power Google Search, ChatGPT, and enterprise AI are not exact. They are carefully engineered approximations. Again, I repeat, the systems that power Google Search, ChatGPT, and enterprise AI are not exact, meaning they're not deterministic. They are carefully engineered approximation or probabilistic, and that is a feature, not a bug. Takeaway 3. The future of AI scaling is algorithmic, not just hardware. The major scaling breakthroughs over the past decade, retention, RAG, efficient attention variants, have been algorithmic insights, not bigger chips. The next wave will likely involve better algorithms for navigation. navigating the non-Euclidean semantic spaces, differentiable approximate attention, and geometric representations that go beyond single vector embeddings. The closing statement on this slide says it plainly: the future of LLM scaling won't just come from more GPUs, but from algorithmic breakthroughs in mapping and searching non-Euclidean spaces. The fractal algorithm, the nearest neighbor search running at every scale from the database to the token, is not a detail of implementation. It is the load-bearing mathematical structure of modern AI. Understanding it is understanding where the field is going. Thank you for your attention.